In this problem, we have a balanced three-phase YY system. The total power dissipated in the lines is 650 watts. V cap AN, which is the voltage at the load, is 117 at an angle of 15 degrees volts RMS, and the power factor of the load is 0.88 leading. If the line impedance is 1 plus J2 ohms, determine the load impedance. And since we're given a balanced three-phase system, we can use our problem-solving strategy entitled Three-Phase Balanced AC Power Circuits. And we're given a YY system, so we don't have to do any conversions. The second step of our problem-solving strategy says draw the A-phase circuit. So here is the A-phase circuit. We have Z load. We know the voltage across Z load. And there's a line impedance. Now, one thing we'll note, line loss in the A phase is going to be 1/3 of the 650 watts. Okay, so we were given the total power is 650, and we'll know in the A phase, in this diagram, there's only 1/3 of that is dissipated in the A phase. So for instance, we can find the magnitude of this current now. So we have 650 over 3 is equal to the magnitude of that current squared times 1 ohm. Okay, and that's because we have a 1 ohm resistance in the line. So then the magnitude of our current is 14.72 amps RMS. So we just went through and solved this equation. Now, we can find the magnitude of Z load. It's going to be the magnitude of V cap AN over the magnitude of that current. So it's 117 divided by 14.72, and that's 7.95 ohms. And then the last thing we need to do is get the angle of the impedance. Now, we were told that the power factor of the load is leading. And if we remember, theta Z for the load is related to the power factor by the cosine inverse of 0.88. Now, it has to be minus this time because it's a leading power factor. Okay. Leading power factor indicates capacitive load, which says the angle on Z is negative. So this gives us minus 28.36. So then Z load is the magnitude of 7.95, an angle of minus 28.36. And in rectangular form, that's 7 minus J, 3.78 ohms.